Welcome to the lab, everyone. As you can see from the glowing holographic equations and 3D models floating around us, we are taking things to the next level today. We're immersing ourselves in the fascinating world of Class 12 physics to demystify the macroscopic science of thermodynamics. This is the incredible branch of physics that governs thermal energy, where work is converted into heat and heat right back into work. So get ready, because we are going to completely change how you view the energy of the universe in this explainer.
I want to hook you right away by asking a really fundamental question. Is heat a fluid flowing between objects? Seriously, think about it. Imagine a hot object and a cold object touching. Is there some mysterious, invisible liquid pouring from the hot one into the cold one, kind of like water equalizing between two tanks? Well, for a really long time, some of the greatest minds in science actually thought the answer was absolutely yes. If you look on the left, we have the old, totally debunked caloric theory. That theory claimed heat was this fine, invisible fluid called caloric that basically just filled up the empty pores of a substance. But on the right, we see the modern truth. Benjamin Thompson, also known as Count Rumford, completely shattered this caloric theory back in 1798. He observed that boring a brass cannon with a blunt drill generated enough heat to actually boil water. Now, if heat was just a fluid, a sharper drill should have scooped out more of it, right? Instead, the heat depended entirely on the mechanical work done by the horses turning the drill. It's a brilliant experiment that proved once and for all that heat is a form of kinetic energy, not some invisible liquid.
So here is our roadmap for today's explainer. We're going to cover the true nature of heat, the Zeroth Law, heat versus internal energy, the first law of thermodynamics, specific heat capacity, and finally, thermodynamic processes. Let's dive in.
Chapter 1: The True Nature of Heat.
To truly understand thermodynamics, we first have to recognize that it's a macroscopic science. It doesn't obsess over the individual coordinates and velocities of trillions of microscopic particles. Instead, it looks at the big picture, the variables we can actually feel and measure. But there is a super important distinction we need to make between mechanical energy and internal energy. Picture a 3D hologram of a bullet fired from a gun. The mechanical state of that bullet, its overall kinetic energy speeding through the air, is completely separate from its temperature. When that bullet violently pierces a piece of wood and stops, its macroscopic kinetic energy vanishes. It gets converted into internal energy. That internal energy, which we represent with the letter U, is the disordered, random, microscopic motion of the molecules inside the bullet. And it's that microscopic chaos that actually dictates temperature.
Chapter 2: The Zeroth Law.
Before we can even measure energy, we have to define what it actually means for a system to be at rest or in equilibrium. In mechanics, equilibrium means net forces are zero. But in thermodynamics, it means macroscopic variables, like pressure and temperature, simply stop changing over time. Let's look at this digital simulation. On the left, we have two gases separated by an adiabatic wall, which is just a fancy term for an insulating wall. Energy can't flow through it, so the gases stay at their own distinct pressures and volumes. But on the right, we swap that out for a diathermic, or conducting wall. Instantly, heat energy begins to flow. The macroscopic variables of those two gases will spontaneously change until they equalize and settle down. Once that flow stops entirely, the systems have achieved thermal equilibrium.
And that brings us perfectly to the Zeroth Law of Thermodynamics, which R.H. Fowler formalized in 1931. It simply states that if System A is in thermal equilibrium with System C, and System B is also in equilibrium with C, well then A and B must be in equilibrium with each other. I know, it sounds like simple logic, right? But this very law is what gave birth to the formal physical concept of temperature. Temperature is simply the physical marker that dictates the direction of heat flow until that state of equilibrium is reached.
Chapter 3: Heat versus internal energy. Okay, it's time to share an insider secret of physics that, honestly, a lot of elementary textbooks get completely wrong. Let's bust a common myth right now. Internal energy is a static state variable. A gas has a specific amount of internal energy at any given exact moment. Heat, on the other hand, is strictly energy in transit due to a temperature difference. A gas does not contain heat, just like it doesn't contain work. Heat and work are simply two different delivery modes used to alter a system's internal energy. You can increase that internal energy either by applying heat from a hotter body or by doing mechanical work, like physically pushing down a piston. Chapter 4: The First Law of Thermodynamics. Now that we have our vocabulary locked down, check out this glowing equation floating right here. This is the core dynamic of energy transfer. Delta Q equals delta U plus delta W. This is the first law. It tells us that the heat energy supplied to a system, delta Q, doesn't just mysteriously vanish. It actually splits into two separate jobs. Part of it goes into increasing the system's internal energy, delta U, and the rest of it is used by the system to do actual work on the outside environment, delta W, like a steam engine pushing a heavy piston. Energy in equals energy stored plus work done. It's wonderfully elegant, and it brings the pure magic of the conservation of energy truly to life.
Chapter 5. Specific Heat Capacity. So, you might be wondering how much heat is actually required to change a system's temperature. Take a look at this data. Notice how aluminum requires 900 joules of energy to raise 1 kilogram by 1 Kelvin, while copper only requires 386 joules. Different substances need vastly different amounts of energy to get hot. This relates deeply to the equipartition of energy, basically how energy distributes itself across all the microscopic translational, rotational, and vibrational motions of the atoms locked inside a solid. Now, this concept gets even more interesting when we look at a familiar substance, water. Look at this animated graph. It shows that the specific heat of water actually varies slightly depending on its starting temperature. Because of this precise, measurable variation, physicists realized that the old unit of heat, the calorie, was just way too imprecise. Today, we've entirely retired the calorie in favor of the joule for all forms of energy. This means that the old term mechanical equivalent of heat is completely superfluous in modern physics. Energy is simply energy. Finally, Chapter 6, Thermodynamic Processes. We can apply the first law mathematically to 4 specific quasi-static scenarios. Let's break them down. Isothermal means the temperature remains totally locked and constant. Adiabatic means the system is perfectly insulated, literally zero heat flows in or out. Isochoric means the volume is locked in place, so our gas can't expand to do any work. And isobaric means the pressure stays constant while the volume and temperature fluctuate. As you'll see, the first law adapts beautifully to every single one of these unique conditions. Let's map this out visually. Follow the curves on this animated graph. The upper, gentler curve represents an isothermal expansion. That's Boyle's law in action, where pressure and volume are inversely related at a constant temperature. But look at the much steeper curve right below it. That's an adiabatic process. Because absolutely no heat is allowed to enter the system from the outside lab, the gas has to spend its own internal energy to do the heavy lifting of expanding. And because it's spending its own energy, its temperature and pressure drop way more rapidly. We've seen how energy is perfectly conserved and how it naturally flows to reach equilibrium. But wait, why doesn't a hot cup of coffee spontaneously absorb heat from the surrounding room and just start boiling? Well, that leads us to this incredibly provocative thought by Rudolf Clausius. No process is possible whose sole result is the transfer of heat from a colder object to a hotter object. Energy has a strict direction. The universe has a strict arrow of time. This absolute, unavoidable limitation on energy transfer is the very foundation of the second law of thermodynamics. But to uncover the deep mysteries of entropy and why the universe behaves exactly this way, well, you'll just have to join me in our next explainer. Keep wondering and keep learning.